Okay, let's take a look at review problem 4.14. For this problem, we have a number of trials that are done where there is a probability of success, but I don't know what the probability of success actually is. There is some probability of success P, which is uniformly distributed between 0 and 1, but it is unknown. And we are also given that we do something over and over again. And so the conditional distribution of x, when I should have said here, x is the number of successes in n trials. And we're given that the conditional distribution of x, given that capital P is equal to little p, is binomial with parameters n and p. So if I know the value of x, if I know the value of p, then the conditional distribution of x is binomial. This question asks for the reverse. Suppose I know the number of successes, what is the conditional distribution of p itself? So this is basically a Bayes rule problem where I'm given one conditional probability and I'm supposed to find the other. So I want to find the probability, and I'm going to write my probabilities like a paragraph symbol for this problem, just to distinguish probabilities from the random variable p. I want to find the probability that my random variable p is in some little interval dp, given that capital X is equal to k. So that's the posterior distribution, the conditional distribution of capital P, given that x is equal to little k. Okay, so I will apply Bayes' rule to this, and I'll get Bayes' rule in a couple of steps. There's a formula for this, but I just want to go over how the formula is derived. That's the probability that both events happen, the probability that p is in some interval dp, and that x is equal to k, divided by the probability that x is equal to k. Okay, now this is equal to the probability that p is in some little interval dp and x is equal to k, divided by, now by the law of total probability, the bottom here can be written as the integral from 0 to 1 of the probability that p is in some little interval du. I'll just use a different letter here instead of p, and x is equal to k. And I integrate this over I integrate this over all possible values of u. Okay, now I apply the multiplication rule again to complete Bayes' rule. So the top is equal to the probability that p is in some little interval dp times the probability that x is equal to k, given that p is in some little interval dp. And then I do the same thing on the bottom. Integral from 0 to 1, the probability that p is in some little interval du times the probability that x is equal to k, given that p is in some little interval du, integrated with respect to u. Okay, now this first bit here is the PDF for the uniform distribution. Well, the PDF for the uniform distribution is simply 1. So this is equal to just simply 1 dp times the probability that x is equal to k, given that p is in some small interval dp that is binomially distributed by the assumptions of the problem. So n choose k, p to the k, 1 minus p to the n minus k. On the bottom, we have integral from 0 to 1. Once again, I have 1 du times n choose k, u to the k, 1 minus u to the n minus k du. And so if I start canceling, I have n choose k's cancel. And so what's given is that, or what I have is that the conditional distribution of capital P, given that x is equal to k, dp is equal to p to the k, 1 minus p to the n minus k, divided by the integral from 0 to 1 of u to the k, 1 minus u to the n minus k du, and then I have this extra dp over here, and that kind of cancels the dp on the left-hand side. So therefore, the conditional PDF of capital P, given that x is equal to k, equals, now the bottom here I recognize to be the beta integral. So this is equal to 1 over the beta integral evaluated at k plus 1 and n minus k plus 1, adding 1 to both exponents. Then I have p to the k, 1 minus p to the n minus k, and the possible values are still between 0 and 1. And I recognize this to follow the beta distribution. So the conditional distribution of capital P given that x is equal to k has the beta distribution with parameters k plus 1 and n minus k plus 1. Okay, now before leaving this problem, I wanted to talk about something that was not asked for in the problem, but just to point out. Let's figure out the expected value of p given that x is equal to k. The expected value of p given that x is equal to k. Using the properties of the beta distribution, the mean of this is equal to k plus 1 over k plus 1 plus n minus k plus 1. So that's the general formula goes r over r plus s. And so this is equal to k plus 1 over n plus 2. And therefore we can write that the expected value of p given x is equal to x plus 1 divided by n plus 2. Now this is slightly counterintuitive. If we did n trials and we have k successes, we would expect that the expected value of p would be something like k over n. And it's close, but it's k plus 1 over n plus 2. So all this is to say, if I simply took k over n to be my estimate for p, that would actually be what's called a biased estimator. And that's a concept that if you take Math 4650, you'll learn more about biased estimators in the context of statistics.